Okay, so just a quick review as to the discrete equivalence. Okay, the objective or the whole idea is giving a continuous block, and how do we approximate that? Okay, or even not approximate, better just exactly the same, and basically how to convert that into a block of g of z, and at the same time, so the g of z will try to retain the same kind of dynamics or characteristics of this continuous block. So what we have covered essentially three different approach. The first one is essentially what's the first one. What you do is you just obtain g of z equal z g of s. Okay, so this is one approach here, right? When we learn Z transform, this is exactly what happened at the beginning here. We said, okay, just obtain a Z transform of doing this one here. But you got to understand, what does this mean in here? For this one here, I'll call it impulse invariance approach. Okay, impulse invariance. So this is essentially the results from the Laplace from the Z transform table. So when you do this one here, the underlying meaning is essentially what you're doing is this is equivalent to say g of t, and this is equivalent to say it's g of kt. Right, it's equivalent. Okay. So for this particular approach, it's like you consider this g of z, as a signal, or so you then sample that, with a certain sampling time. Right, so you have this signal here, and you pass through an impulse sampler. Then you got a sequence of impulses, right? Then you take the Z transform, and you get g of z. So this is called impulse invariance. All right, yeah. And for this particular approach, and we generally what we see is this one retains the impulse response of the original system very well. Okay, so but the phase is not as good as the other one. Second one here is called zero order equivalent. So basically, for this particular case, your g of z is converted as if you have a zero order hold in front of this g of s. Okay, g of s. So this is zero order hold equivalent. For the second approach, usually you apply this equivalence when you're trying to discretize a plant. Okay? So when you have a plant, and you can use this to discretize a plant. Okay? And third approach, in general, is called numerical approach. And we cover three different numerical approach. And the first one is called Tusting's method, or you can also call that trapezoid. Okay, so basically the area is approximated using a series of trapezoids, right? Yeah, and we derived that for 1 over s, you can use this big guy here to approximate this 1 over s. So equivalently, if you take a reverse of that, so basically s can be approximated using this 2 over t z minus 1 over z plus 1. Alright, so that's testing. And we also had a forward difference. Okay. For forward difference, you're using rectangle, but you're using basically the previous value to create a rectangle. And we derive that this 1 over s is t over z minus 1, or s is z minus 1 over t. Okay? So this is forward, and then we have backward difference. Okay, backward difference. So backward difference is you use the current value and then create a rectangle right back to the previous instant. And 1 over s is approximated using zt over z minus 1. Okay? Yeah. Or equivalently, s is z minus 1 over zt. So those are three different numerical approach, okay, for approximation. Okay, yeah. Yeah.
So I'm just wondering, what's like the advantages and disadvantages of using one over the other?
Yeah. That's a good question. You know, this is actually not an easy question to answer. So what I want you to do is this. Yeah. What you can do is try to use a Simulink. Okay, so you have a signal generator, right? So let's say you generate certain kind of a sinusoidal signal, right? Yeah. And then you create this 1 over s block. Okay, yeah, that's integral, right? Yeah. And then you create basically 3 other blocks. Okay, 3 other blocks here. So one block, let's say this is testing. Basically, you plug those, you know, this those things over here, right? Testing, forward difference, backward difference. Okay, yeah. So fit it to each one of them and display it. Okay, yeah. See what's the difference, right? Yeah. So the difference generally, this is one way to look at the difference. Okay, this one we're looking at difference, and the other way looking at difference is, okay, is to look at the frequency response. So you have the original system, and then you have this discrete corresponding discrete equivalence. So you look at the frequency response of the original one and the frequency response of the converted one, right? So frequency response meaning you're looking at the magnitude and the phase, right? So you compare, basically, you look at what will be the difference. So generally you will see the difference on the frequency response quite well, because at a certain frequency there's a good match, and after a certain frequency you start to see the difference, basically. Okay, yeah. But bear in mind is what happens is, right? We call it equivalence, but it's not exactly the equivalence. Okay, it's not exact. It's always approximation. Okay, so there's no exact match between the digital part and the continuous part. So you always lose something. So each one of them, there are advantages or you know, benefits of themselves, but there are also disadvantages for some of this. So you gotta play around with it. I do have a table though, kind of summarize this thing here. Really, I didn't want it to go into that topic. It's actually gonna take a while if I really wanted to go into here. Let me see, do I have not this one here. Here is the table. Let me show you the table here. So this is a table here. A little summary here. See, for example, 0 order hold. You want an exact discretization in the time domain for staircase input. Okay. And the impulse invariance mapping is you want an exact discretization in the time domain for impulse stream input, right? That kind of makes sense, right? So what does that impulse do? This one here, right? It basically does is it takes the Z transform for this one. That's when you have this impulse stream input, right? And the 0 order hold is you have a 0 order hold in front of this plan G of S. So the input to the G of S is a stared input. Right, stair input. Okay, yeah. Other things, you know, for example, testing. So testing actually it's an interesting one. Testing is you have a good match between the frequency. So when you have match, basically you have the S plane, you have the Z plane. When you map from the S plane to the Z plane, you have exactly the same kind of match. Okay, yeah. So that's the testing. So I'll probably have something here in my lecture notes, and it's not the key point. I want you, if you have a time, you can take a look at a reading of that portion there. So this portion, yeah. So this one here. So from here, the mapping, this portion, the numerical one, the mapping, right? This paragraph here. How does the mapping occur between this between the S and the Z? Given this numerical approach, okay, yeah. So maybe I'll give you one simple example here, right? I'll give you one simple example, just shortly explain what this mapping does at here. So let me copy one of this one here, okay? And then tell you what this means. Yeah. Okay, so what this one does is, this is a forward difference. Okay, this is forward difference. Okay, so this is a mapping. So here is S-plane, and this is a Z-plane. Okay, here's S-plane. Okay. So given S-plane, with continuous system, we learned where is the stable region for a continuous system. Under the S-plane, left side, right? Left side. Okay, yeah. So what's the forward difference mapping? Which is this one here, right? Which is this one, okay? So if I rewrite that slightly, and I will get, okay, Z equal, okay, ST plus 1, right? So this is a forward difference. So this is the connection between Z and S based on the numerical approach forward difference. All right? Yeah. And actually, by the way, what's the connection between Z and S when you use this impulse invariance? When you use this one? Yeah. Come again? Z equal to E ST, right?
That's like the basic definition, right?
That's this conversion between when you have an impulse sampler, basically doing an impulse sampling to a continuous signal. Right? Remember, this is x of t, x star of t, and then we have x of s, x star of s, and x star of s is transformed to x of z by substituting the s with 1 over t long in z, right? Do you remember that, right? Yeah, so this is a conversion at here, okay? Yeah, actually we're going to talk about this conversion or this mapping in detailed probably 1 or 2 lectures, okay, later, okay? But for time being, let's come back here, okay? This is a forward at here. So where would this left side here be mapped into the z corresponding z plane? Okay, where would that be? So it's actually this left side of the S plane here is going to be mapped into this shaded area here. Okay, so it's going to be mapped here. Okay, so that's the in the figure on the textbook, that's what it means here. So the left side of the S plane is going to be mapped into this shading area at here. Okay, so what does that mean is this circle is a unit circle. Okay, this circle is a unit circle, and this is a unit circle in the Z plane. Now remember, what is unit circle? What's the significance of unit circle in the Z plane? It's the what? Under Z plane, you're talking about Z minus certain poles here, right? And maybe another one, who knows, right? Okay, yeah. And if you take a inverse Z transform, and what does that give you? That basically gives you a pi to the power of k, right? So if we want it to be stable, this value has to be less than 1, or the absolute value of this has to be less than 1. So which means as long as you are within the unit circle, you are stable, right? So that's the significance of this circle here. But however, you can see now the mapping from the left side of the stable S, it's not mapped into this unit circle here, right? It's actually everywhere in the Z plane. Okay, so basically this is what happens under that word there. So when you have a continuous when you have a continuous stable pole, okay, and when you have a continuous stable pole, it could be mapped Okay, it could be mapped to where? To a unstable Z pole. Okay, that's what this is here. I'll show you an example. Could be mapped to an unstable, okay, then there's a pole in Z plane. Okay, in Z plane. Okay. So here's one simple example, right? For example, let's say my S equal to -2 plus 2j. Okay, is that stable? That's a stable, right? Because y -2 is on the here. Okay, yeah. So now if I do the mapping using forward difference, so what will be the Z location of the pole? It will be ST plus 1, and that gives us what? 1 minus 2t plus 2j, right? 2tj, right? Okay, yeah. So suppose your t is 1.5 seconds. Let's see. So where would that be? You plug in 1.5 here. The real part of the real part actually, once you plug in there, you'll see that Z is outside that unit circle. Okay, outside unit circle.
Is that a good thing? That's not a good thing.
That's not good, right? That's basically you have a you have a stable pole. Let's say S here is minus, this is plus 2 minus 2j. Yeah, right? So they usually appear in a pair. So maybe there's another one plus 2j. Okay, so this is a continuous system, suppose, right? You design your continuous system. This is your closed loop, and you have two poles, a pair of complex poles. Okay, and they are stable, okay, because they are on the left side. Okay, and now you're trying to use this forward difference to do the conversion. So what you do is you let S equal to this guy here. That's what you do for the equivalence, right? Yeah, and then you find that, and you set your time, you set your sampling time as 1.5 seconds, okay, or some other seconds, right? So you will find that your Z, the corresponding poles, okay, after the conversion, okay, after the discrete conversion, discretization, it's outside the unit circle, right? So that's basically a bad thing happens, right? Yeah.
So for stability in the Z plane, if you use the forward difference method, it has to be in the left-hand plane and within that unit circle?
You can't guarantee that. See, this is the wording here. Why is it called numerical approximation, right? This is why it's called approximation. Basically, it's only good to a certain degree. Okay. So when you use approximation, this is what you have to bear in mind. You're not exactly describing the original dynamics of the system, right? So you shouldn't expect to get. If you use a numerical approach, you shouldn't expect to get exactly what's going to happen as to the continuous system. Okay? Yeah.
So to make that problem stable, you increase your sampling frequency.
Yeah, that's true. But if you can't, you said my sampling time has to be this, then you can't use that forward difference, right? Yeah. So you have to choose basically an appropriate ones to do this deconversion. Okay. Yeah. Okay. So take a look at this one here. But there is this for testing. If you look at the lecture notes, okay, for testing one, the testing is the left side of S plane is mapped exactly to the inside of Z plane. It's testing also called bilinear. So testing has this neat one-to-one kind of mapping in testing one here. Okay. So this is why testing approach often in time used a lot in discrete equivalence when you're converting a continuous controller to a discrete controller, right? Yeah, so the testing approach. Okay, so what I need you to at this stage to remember is, okay, a couple things. Remember, in this lecture, what we're going to do is when we're trying to discretize, we normally what we're saying is we're trying to discretize a plant. You're going to stick with this one here, okay? Stick with this. If you're required to discretize a controller, then you're probably going to choose one of the methods over here, right? Yeah. If you're gonna actually doing something, actually will be involving this one here, involving a pose, looking at basically the system response, looking at comparing the response of the discrete system with the continuous system. We're gonna actually look at this one here, right? Yeah. So, giving a final example is, so let's take a look at the example. Let's see if I have a PID controller, continuous PID controller, and how do I get a corresponding digital PID controller? Okay, so this is basically the first kind of controller that you see. So for continuous system, if you have a PID controller, so what does that look like? Let's say if I have a PID controller and there are 3 gains. Okay, that's PID, right? And this E of t multiply k, so k is proportional. Okay. Then this k over ti, so that's generally what we call integral. Okay. So the ti, so we call the integral time. And this ktd, that's what we call the derivative. Okay, derivative. So this is typical PID controller. So what happens is you integrate this error, okay, and this portion is to take a derivative of the error, right? So you should remember the effect of each one of the gains that are here, okay, and integral part is trying to decrease the steady state error. Derivative part is trying to add in damping into the response, okay, yeah, and the proportional part is trying to increase the response time, right? Yeah. So there's often in time the integral gain at here will decrease the system stability. The derivative term will basically add stability into the system, right? Damping, what does damping do? Damping it to slow down this response, right? So those are continuous systems here. And now, if we want to have a digital PID, so what you can do is you can simply convert this one, okay, and discretize this using the numerical approach that we have just learned over there, right? Yeah. So for the second one here, and when you take Laplace, this is basically 1 over s, right? And when you take a Laplace here, this is the s term and here. Okay? That make sense? Yeah. So if you take a Laplace transform, basically it's m over ms, right? Over e over s, okay, over e of s equal to k plus k over ti 1 over s plus ktd s. Okay. So that's the continuous transfer function for the PID block. And if we wanted to discretize that, so that all you need to deal with this and this at here. Okay, these two. So which one should I choose then? So this 1 over s, let's say I'm going to choose the testing method or the trapezoid method for this 1 over s, right? Yeah. So which means we are going to get, okay, discretized, okay. So we're going to use this testing at here. Okay, we're going to use testing at here. And for this one, S at here, I'm going to use the backward difference. Okay, backward difference. Yeah. Good point. Yeah, why would you not, right? Let me write down this one here, and I'll kind of explain this here, okay? So this K over Ti, testing 1 over S, what was testing 1 over S? So where is it? It's this one here, right? It's this one. So T over 2, Z plus 1 over Z minus 1. Okay, yeah. And this S here, if I use backward, and that will be Z minus 1 over ZT. Okay, yeah. Is that okay? Yeah, that's basically nothing tricky here, just bring it here. Okay, so now back to the question here. Why don't you use this testing for the S here? In other words, if you use the testing for the S, what do? You basically invert this one here, right? So if I use testing, then what would that be? So this would be K 2 over T Z minus 1 Z plus 1. That make sense? Right? Yeah. Not that you can't use it. Yes, you can. Okay? But however, there is a little potential problem here. If you look at this one here, what's the pole at here? Negative 1. Okay? Yeah, so you have a Z equal to negative 1 in here, right? Negative 1. So then you think about what happens once you insert this controller to the system. So when you insert this one into the system, you have a pole of Z equal to negative 1, right? So basically, when you do partial fraction expansion, you have a Z plus 1 and Z something else, and then there's something at top over there, right? When you do partial fraction expansion, you will have maybe certain kind of things like this. That make sense? And then the inverse of the Z transform of this one will be giving you what? It's negative 1 to the power of
K.
Exactly, right? The power of K. So what does that one? What's negative 1 to the power of K behaves like? What does it behave like? Exactly, right? It alternates between this and here. Okay? Remember what this does. This is your controller, right? This is your controller. And the controller behaves, or the behavior is determined by its pole. If the pole shows this, means your controller will have a behavior of up and downs, right? So your control input, at this moment you want it to be 5. Next moment, negative 5. And then that moment is 5 again, and negative 5 again. You know what I'm saying? Right? So, in other words, your input to the system is probably showing this kind of behavior. Okay? Yeah.
Then you want to avoid negative poles in the Z.
Yes. So basically, this is called a ringer effect. Okay, a ringer effect. So you don't want, so the rule of thumb is you don't want to input your system like an oscillating kind of things. So why is that? Because let's say you have a motor, and your motor feels this oscillating. One moment is here, one moment is that. So this basically is trying to do this, right? And that's kind of damaging basically to the system. Okay, yeah. So you want your control input to be smooth, right? So you don't want to be. Sometimes you can't avoid this. You have to do this, right? But you don't want to manually or to have this kind of purposely to have this, and then to have this one here, and that's not good, right? Yeah. It's okay? Yeah. So not that it's not going to work, right? It's still going to work, but so basically sometimes from the output response, you won't see this here. So the output looks absolutely okay, right? You know, the output is stable and it's there. But however, when you look into the control input to the system, and you see this kind of linear things effect, right? And that's not good to the system for a long run. Okay. Yeah. Good. All right. So there is an example. I want you to play with that. Okay. There's an example of implementing a digital control, this PID. Okay. So you combine everything that's your PID. You implement the digital PID to a simple system like this here, right? Like this here. Okay. Do a simulation using either Simulink or using MATLAB. So I have a script file here, not a Simulink. So you can build a Simulink block trying to do the same thing, okay? And trying to adjust the gains. Trying to adjust the gains. The key here. Where's the gains here? The K, Ki, Kd. Trying to adjust the gains and see what's the effects of changing gains. So this kind of controller, that's basically what you're going to be able to implement on our the experiment setup, right? Yeah. Is that good? Okay. So this is basically the end of this discrete equivalence, okay? And then let's talk about a new topic here. Okay, so we're going to shift the gear a little bit. Okay, we're going to shift to a slightly different domain, and I call that state space approach. And we'll come back to this Z thing later, all right? Yeah, we'll come back to this a few lectures later. But the new topic is state variable method. Okay, state variable method. Okay, so we can also call state space method. It's fine. Okay. So for people who are taking modern control, so some of the topic here would be very familiar, right? Yeah. But you might notice some difference, okay, between the results are presented here and maybe the results when you learned in modern control. So let me talk about the state variable first, okay, and then we'll look at how do we obtain the state space model. Okay. So suppose that I have a system, okay. Then when you describe a system, right? So when you describe a system, let's say I have a mass print damper system. So that the equation motion is mx double dot plus kx bx dot plus kx and equal to an input. Nice, right? Input. So when you look at this system here and you see, okay, I have a system parameter mbk and I have input, right? So this is basically how you would describe the system. What does x mean? X represents the position, x dot represents the velocity, right? X double dot represents this acceleration, right? Yeah, so this is one way of describing the system here, okay? Now, the other way of describing the same system is instead of using what you so-called x dot, x double dot here, so you can also see that I'm going to use a so-called a set of state variables. Okay, so we're going to use a set of state variables to describe this system. So the set of state variables in general, let's say I have x1 of k to xn of k. So we're talking about discrete time system, so we're using k at here, right? If you continuous system, then use t. So I'm going to use set of state variable to describe system. So inside this block here, so we use these state variables here. Then we have maybe a multi-input to the system. So this is a SI, single input, single output here. But in general, you may have a multi-input to the system. Maybe the first input is U1 of k, U2, and maybe up to UR of k. So there are inputs. Okay, there are inputs. And there are n number of states. The n net here generally is associated with order. Okay, so this is the order of the system. Okay, it's order of the system. And at the same time, you may have a multiple outputs at here. So let's say y1 of k, y2 up to yp of k, right? Yeah. So this is another way of describing a system. Of course, you might. So where is that set of state variables from, right? And how do you use appropriate set of state variable to describe system? That's actually what we're going to cover. How do you choose the state variable? Okay. But for right now, I can tell you is there are infinite. There are infinite number of way. Right? The keyword is infinite. Okay. There's not just one way of picking a set of a state variable. There are no limit, okay, of picking state variables for the same system. Okay, yeah. So for this kind of system, I call it MIMO, so multiple input and multiple output system, so MIMO system. Right? Even though in our case we will focus on is a single input and a single output system. Okay? But right now, let me give you so for SISO, which means this R equal to P and equal to 1. Okay, and that's SISO system. So the state variable, okay, we said it's infinite, but you cannot pick it arbitrarily, right? You don't pick it arbitrarily. You have to pick your state variable such that, okay, they represent, okay, the so-called minimum amount of information. Okay, minimum amount of information to describe the system. Okay. Okay. So we'll look at how to properly pick the state variable. Okay? The state variable here. But in short, if you look at the state variable here, x1 to xn, so we're going to use the vectors. From now, you will see a lot of matrix and vector concepts. So I'm going to use vectors to represent this state variable. Often in time, what we do is, okay, we often use this column vector, okay, to represent this one here. So in mathematics, there's a war between column vector and the row vector. So sometimes people use the row, sometimes use the column, and we'll use column vector here. Now you can rewrite this one just slightly. Okay, so you can write it in a row, but you have to put a transpose at here, right? Yeah. Okay, so was that clear? Yeah, that's basically the kind of idea state variable here, right? Yeah. Now then, in terms of the mathematical expression here, then given a system, right? Given a system, here is the general formula, okay, or equation for a system here. Okay. For a general system, which means the system may be nonlinear, okay, which may be nonlinear or may be linear, and the equation of motion or the equation describing a system using state variable approach will be in this format at here. Okay, it will be in this format. So what this means, basically, we're dealing with discrete ones, okay, and if it's continuous one, it will be slightly different way. So for continuous one, it will be x dot t equal to f of x of t and u of t, right? This is a continuous one. This basically saying is the next moment, x is a state here, right? X is a state. The next moment of a state value, okay, state variable value, is a function of the input and the previous value of the state variables. Okay, yeah, that's what this means here. And you also have the output, right? You also have the output here. So the output can also be written as a combination or a function of this state variable and input vectors. Okay, input vector.
Is that n bar?
Pardon me?
Is that n vector?
U is vector.
U?
Yeah, because our input could be multiple inputs here, right? The inputs could be multiple. Yeah. So maybe let me write it down here. So the U up to R, so there are number of inputs, R number of inputs here, right? Okay. So this is just the general formula for general system, dealing with either linear or non-linear. However, if we're dealing with LTI system, which is what we're going to deal with, okay, and we have a simpler expression here. So for LTI system, okay, for LTI linear time invariant system, what you have here is x k plus 1 equal to a xk plus b uk. So this is basically the corresponding part of this, right? So now you have specifically an expression here. So that's still a function of x and u, right? Yeah. And your y is c x of k, okay, plus d u of k. Okay. So for LTI system, you will be able to have this kind of format to describe it. Now this is what we call the state space equation. Okay, state space equation. Okay, state space equation. So this essentially opens a door here of analyzing a system using a different approach. And in your control system generally, what we have been dealing with a Laplace transform or time domain or differential equation, right? Yeah. So those are one way or another of dealing with the system. So now this is another way. Basically, this is called using state space method to analyze a system. Now, what are the A, B, C, D here? Those are so-called system matrices, and particularly A and B there, all right? Yeah. And the A here is a matrix. So what's the size of matrix? So if X is a n by 1 vector, you look at this one here, that's so-called, okay, when I write this one here, I mean this is an n by 1 vector, and each element of the vector is a real number. Okay, so this is what it means here. Okay? Yeah. So this is the n by 1 vector. And coming back here, that's A matrix is a n by n vector matrix, and it's real. All right? It's real. Yeah. So. And the B. So what's B then? Let's say the U. What's a U? U is a R of U is a R by 1, right? There are R number of inputs at here. So U is R by 1. So the B, it's not arbitrary size, has to be what? N by R. Okay, N by R. Does that make sense? See, when you use a n by R matrix, multiply by R by 1, what do you get? You get n by 1, right? Yeah. So the size has to match. Size has to match the matrices. The C matrix works with this. So the C matrix is a so-called selection matrix. Because why? Because ultimately, what comes out of this expression give you what? This is output, right? This is output here. So you're actually getting output out of this expression. Then the C at here is R. This is n by 1. So the C is actually so-called P by n. Why is it P by n? Because what I showed you here, there are P number of outputs at here, right? P number of outputs. Okay, yeah. So P by n multiplied by n by 1, you get a P by 1. So that's the size of this vector at here. Okay, yeah. And the D at here, okay, the D at here is a P by R size. Okay, P by R. Often in time, the D is going to be 0, right? It's going to be 0. So D is actually a forward term. Okay, so generally it's going to be 0. Okay, yeah. So in our case, so D will be 0. Okay, in most cases. Was that good?
Just got a question.
Yeah.
So what's like the physical significance of the D term? Like
it's a forward. It's a forward thing. So let's say this is input U here, right? Then the U at here multiplied by this D. Okay. Then here's a junction at here, and maybe R. This is a C here multiplied by X, right? And give it to the junction. What do we get? We get the Y, right? The Y here. Okay. So what does the U do? The U feed it to the system, right? U feed it to the system. So U at here, the D at here basically takes a so-called forward block. Yeah. Okay.
So like in a physical system, where do you generally see it? Like in a, like say you give like a mechanical system, where would your D term come from?
The D generally comes from your design. Yeah.
Okay.
It comes from your design essentially, right? Yeah. Now sometimes if your system also let me see, yeah. If your system, yeah, that's an idea. Let's see. If your system is, yeah, if your system is, just hold on 1 second here. I have this next one we're gonna talk. There's a concept called proper system, strictly proper system, and non-proper system. Okay. So basically, your system is described by transfer function, and there's the order of the numerator, there's the order of the denominator, right?
Mm-hmm.
So the order of the numerator, if the order of the numerator is larger than the order of the denominator, that's called a non-proper system. But if the order of the numerator is less than the order of the denominator, tongue twister, so that'll be a so-called proper system. Okay? For non-proper system, you will have this D at here.
For non-proper.
Yeah, just hold on to the thought there, right? Yeah. Okay? Yeah. Okay, good. Okay, so now we're ready to look at the state variable approach here. But before we do that, I think I need to draw a diagram here. Essentially, is the idea is what do we do with what are we doing with the discrete ones here, and where is the discrete model from, right? Okay, how do you obtain the discrete, okay, discrete state space model? Okay, so this is like actually getting a discrete equivalence, you know, like the previous case, getting discrete equivalence. And here's your continuous, okay, ODE here. Let's say this is your continuous system, and the system described by ordinary differential equation. Right? Okay. And now I was saying is I don't like to analyze the system or to control the system with using the ODE. So I wanted to use a digital controller, and then I wanted to obtain a discrete state space model for this system here. Okay, this is my original system, mechanical system, electrical system, doesn't matter. So what do we do? So there are two different ways of doing it. Okay, the first one is you have the continuous one here, right? You obtain your transfer function. Okay, so the transfer function is the S function, not plus. And then, based on your transfer function, you obtain a zero-order hold equivalence. Okay. Right. So that's what I mentioned at the beginning of the lecture, right? So you put a zero-order hold in front of the block, and you take a Z transform, so you get a Z function. Okay. Then from here, this is what I'm going to show you next. Okay, so this is my next part of the lecture, or maybe next lecture. So next lecture or next part of the lecture. So from here, you get your discrete, okay, state space model. Okay, so you can get your state space model. So basically, what we're gonna learn is we're gonna learn how to get a discrete space model based on the Z transfer function. Okay, yeah. And the other branch is this. So instead of getting a transfer function in here, so you can also get, so from here, you convert the ODE into a continuous, okay, into a continuous state space. Okay, so this is basically modern control, right? When you learn modern control, and the first step is you have to convert your ODE into a state space model, right? Yeah. Then from the state space model, continuous one, we discretize it. Okay, we discretize this. Okay, so how do I discretize that? Well, this is the same idea. So how did you discretize the S block? What did you do? You put a zero-order hold in front of it, right? Yeah. And here, when you discretize a continuous state model, this is actually, I'm going to show you the one lecture we're going to talk about that. It's the same thing. We're going to use use a zero-order equivalent to discretize this continuous state space model. All right? Yeah. So same idea. Okay. So we will end up with this zero-order hold, okay, equivalent, okay, discrete, okay, state space model. Okay, so the discretization is based on a zero-order hold equivalent. Okay, so bear in mind these two branches here. Okay, and these two branches essentially will end up with the same thing. Okay, end up with the same thing. Is that good? Yeah. In this first branch right here, there might be sometimes a little bit of a detour here. When you get your Z transfer function, okay, maybe some people do is they convert the Z transfer function into a difference equation. Okay, difference equation. And that's actually pretty easy. Just remember, how do you convert the Z to a difference? So what you do is you always just remember one thing. Z to the power -1 is one step delay. Okay, right? Yeah. So you obtain your expression, that part I will show you, and then you can get your difference equation. Okay? Yeah. So from the difference equation, and you can get this discrete state space model. Now, if you compare it from here to here, that's equivalent to say from here to here. Okay. So your difference equation is basically the counterpart of the ODE. Right? Okay? Yeah. Good. So now let's take a look at a couple of the concepts here and our examples. Let me kind of show you what I mean at here. Okay. Yeah. So let's see an example first. Let's say I have a system in here. Okay. So what I give you is let me give you a transfer function maybe. So let's see, I have a transfer function. Okay, so here's a transfer function. Actually, you know what? Just a second here. Let me change this slightly. Oh, there's a z squared. Put a z squared here. No. I don't have that here. Just let me say, because I don't have this one here. Let me just make sure I got it. The counterpart of this one here. So what I'm trying to say, I'm trying to use a trans function to describe this one. Okay, trying to do this. So here's the difference equation either way, okay? Here's the difference equation. If I rewrite that difference equation in terms of k at here, this is k minus 2. This is k minus 1. This is k minus 2. Okay, it's k minus 2. Okay. Then in terms of z transfer function, okay, in terms of z transfer function, what do? You basically take the z transform both sides here. You get y of z at here. You get z to the power negative 2 here. You get z negative 1 here. And you get z to the power negative 2 here. Is that right? Yeah. So the transfer function of this system here basically move this square to the left. Okay, take out the common factor and find the ratio between y of z and u of z. So what do we get? Z to the negative 2 here, 1 minus, no, 1. 1 minus 1.7 plus this, right? Plus this. Okay? And this is equivalent to if you multiply both the numerator and denominator by z to the power of 2, what do we get for the top? It's 1 at here, right? Z squared here. Z here. And 0.72 at here. So that's what I showed here, right? Okay? Yeah. Okay, so just a side knowledge at here. So you might wonder is, why did you write this and why did you write this? What's the difference between these two here? Well, technically, mathematically, there's no difference, right? Yeah, but this is normally a DSP format. So if you're an electrical engineer and you practice digital signal processing, they generally like to write the Z transfer function using this negative things at here, okay? Using negatives. So that's more of a DSP standard. But for this one here, what we generate is, this is sort of a, you usually see that in the control application, or as a controls engineer, you generally write the Z transfer function like this. Okay, yeah. However, in our case, we sometimes just use both, right? Yeah. So, can you see the connection now between the difference equation and Z transfer function, right? So giving Z transfer function, you can easily get the difference equation. Okay, it's the same idea as giving a Laplace transfer function. You can easily get a differential equation. Okay, yeah. Now the other thing is, okay, I also need to mention is when you, let's say if you are given a difference equation of here. Okay, if you're given a difference equation, and you are asked to obtain the Z transfer function, the pulse transfer function. So bear in mind one assumption, you have to assume all initial conditions to be 0, right? Yeah, that's the way to obtain the transfer function. Yeah. Same concept to continuous system. You know, when you obtain a transfer function from a differential equation, you have to assume all initial conditions to be 0 to obtain a z function. 246. A lot of people fail one of the last question. So next question is, okay, how do I obtain a state space equation, right? If you look at this branch right here, if you look at this branch, what's this branch? Basically, we're over this branch here, right? We have a z. Basically, we have a z transfer function right here, and we're trying to obtain a discrete state space model, right? Yeah. So here's what we do. I'm going to, okay. Actually, I'm going to do this step from the z to the difference equation. So we're gonna get the discrete space model from the difference equation here. So going this branch here, okay, this branch. Okay, so coming back here, so where's my difference equation? My difference equation, either this or this, doesn't matter, okay? So they're all the same thing. Then here's what you do. You define yourself, or you choose state variable. Okay, so this is a sort of a general approach here. Okay, once you know, you can deal with any kind of difference equation. And what's the order of the system, first of all? Second. So if the second, how many state variable do I need? 2. Okay, good. So the first state variable, I'm gonna choose, okay, this x1 to be y of k. Okay, I'll choose this x1 of k to be y of k. Is that okay, right? So you may wonder, can you choose something else? Yes, you can. Okay, yeah, but as I mentioned, you do have infinite number of solutions or choices. I'm going to choose x2 of k to be y of k plus 1. Okay, x2 of k to be x1, y of k plus 1. Now you also need to bear in mind, what is y of k here? Y of k is the output, right? So now if I compare this second state variable with the first state variable, what's the connection? Right? It's basically x1 of k plus 1. Is that good? Yeah. Okay, so then we're gonna have, based on the second state variable x2 of k here, if x2 of k equal y of k plus 1, then what about x2 of k plus 1? Okay, what about x2 of k plus 1? So x2 of k plus 1 will be y of k plus 2. And then what is y of k plus 2 then? Exactly, that's our original difference equation, right? That's the original difference equation. Okay, so rewrite your original difference equation at here. So this is u of k at here plus 1.7 y of k plus 1 minus 0.7 y over k. Okay, yeah. So that's x2 of k plus 1. You will see that what's the reason we're doing this, okay? Yeah. Okay, so now y of k plus 1, you're coming back to your state variables. What is y of k plus 1? That's what? x2 of k. And what's y of k? x1 of k. So this expression can be written as this. Okay, and this is x2 of k plus 1. Okay, it's 2 of k plus 1. Okay, so then coming back here, what is x1 of k plus 1? So now actually, you know what? I'm gonna just move this down slightly here. Okay, what is x1 of k plus 1? It's what? x2 of k here, right? Is that clear? Yeah. So now I have a set of equations here. And this is a set of equation describing what? Describing the relationship between x1 of k plus 1, x2 of k plus 1, and x1 of k and x2 of k, right? And plus this u of k here. Okay, u of k. Yeah. So then the whole thing at here is, okay, we will be able to rewrite this set of equation. This is linear into a matrix format. And so one side here is x1 k plus 1 here, and the other side x2 k plus 1 here. Okay, and this side here, and I wanted to have this kind of idea. Okay, I wanted to have this, and plus a u of k kind of thing here. Okay, so this is what we want. Okay. So then what will be this matrix here, and what will be this matrix at here? Right. So look at this matrix here. So this matrix, basically this is our A matrix, this is the B matrix. Okay. So to help you look at this a little better here, I'm going to move this u of k to the back at here. Okay, move this u of k to the back. Okay, to the back. And I'm going to rewrite this one just slightly. Going to rewrite this one. Okay, rewrite this one as 0.72. Was it? Yeah, 0.72 x1 of k negative plus 1.7 x2 of k. Okay, so just rewrite the order of the additions here. And we're going to rewrite the top one here as this: 0 x1 of k plus x2 of k. Okay, is that okay? Yeah. So now you can see clearly what will be the matrix now. So the matrix at here, this will be what? 0, and this is 1, negative 0.72, 1.7, right? Yeah. Okay. And the u at here, there's no u on the top, so basically the 0 uk. So this is 0 at here, 1 at here. Okay. Yeah. Now this is the state space equation, right? This is state space equation. And if you wanted to write it using vector format, so basically you can define this as x vector, and this is actually x plus 1 vector, and this is x vector, and that's u vector, but in our case this is just a single input, right? Just a single input. Okay, so we do have one more here in terms of state space model. So basically we're dealing with the output, right? Dealing with the output. So you look at the output here. Where's output? Output is y of k equal to x1 of k, right? So the output, essentially it's the first state variable. Okay, so the first state variable represents the output. Is that good? Yeah. So then the output, it's only the first state variable. So I'm using x of k here. Okay, so this is the vector here. Maybe write this x1 at here, x2 at here. So output has nothing to do with x2. It's only x1. So just 1 0 at here, right? x1 0. Okay. So back to Robbie, to your question. In this one here, do we have the d term, Robbie? So apparently we don't have the d term here, right? Yeah. So why is that? Well, remember what I said. Remember what I said about the order of the system here. So what's the order of the numerator here? Yeah. What's the order here? 2, right? So the order of the numerator is less than the order of the denominator, right? Yeah. So yeah, that's actually so-called strictly proper system. Okay? That's strictly proper. Yeah. So in this case, I don't have the d here. Okay? I don't have the d here. Yeah. So you'll see some cases the d will show up, right? Yeah. Okay, is that clear? So that's how you derive a state space equation here. Okay, so there's no this term. Okay. Now, I need to repeatedly saying this is state space model. Okay, it's not unique. You have infinite number of choices, and regarding the state variable, okay, okay, they don't necessarily have a physical meaning every time. So for this one here, the first state variable represents the output, right? Basically the output, maybe position. So the first state variable is the position, maybe. Okay, yeah. But in some other times, let's say maybe you have x2, x3, x4, x5, all right? So the other ones may not have specifically a physical meaning as to what exactly are they. They're a lot of the time they're just mathematic symbols there, okay, that fit the needs. Yeah. Is that good? So we still have one more time, a little bit more time. Let me show you one more example right here. Okay. So then we'll deal with more general things in the next lecture. Okay, next lecture. Okay, so I'm going to show you a slightly different way of obtaining a state space model. Okay, so here we have a state Z transfer function. Okay, a Z transfer function. Okay, so this is in DSP format here, right? Okay, so if you don't like this format, so let me rewrite it back into the original controls format. And what do? We divide both, not divide, we multiply both the numerator and denominator by z to the power of 2. And what we get is we get z here plus 5 here, z squared 4z plus 3. Okay, so that's the other format. Okay, yeah, the other format here. So, looking at this one here, the numerator order is less than the denominator order, huh? Yeah. So you should expect you're not going to have the d term, right? Yeah. Okay, so I'm going to stick with this one here to derive it. So here's what I'm going to do. I have this y of z here over z equal to this, right? So we're going to rewrite this. So y of z multiplied by this chunk here. So multiplied by this equal to u of z multiplied by this numerator, right? Okay. So y of z multiplied by this denominator, what do we get? We get 4z1 here plus 3 this and that side. Okay, is that. Okay. Is that good? Okay. So then I am going to do this. I'm going to move, okay, this one to the right. Okay, move this to the right. Okay, so and once you moved, and then you do this, right? After you move that 2 terms to the right, so you see there is a z to the power of -1 here, and there's a z to the power of -1 here, right? Yeah. So we can take this. We'll take this z to the power of -1 out. Okay. Then inside here, that becomes u of z, right? That's u of z. Okay. And when you move this term to the right, this 4 becomes -4. When you take the -1 out, so that's just -4 y of z. Is that cool, right? Yeah, very good. Okay, so then here's z to the power of -2. So I'm going to take another z -1 out. Okay. Yeah. Nope. So I'm putting that in one big bracket. So you see, this then negative 1 multiplied by that, then z to the number negative z to the power of negative 2. Okay? So this is what happens after little modification. Okay? Is that clear? Okay, so now I'm ready to define my state variable. Okay, my state variable. So we're going to define this x1 of z. Okay, x1 of z equal to this, equal to z to the power of negative 1 u of z minus 4y of z, and we're going to call this whole piece right here as x2 of z. Okay, x2 of z plus x2 of z. Okay, yeah, so that's x1 of z. So now you know what x2 of z is now. So x2 of z is z negative 1 here, 5u of z, 3y of z. Okay, yeah. So that's the two state variables. Okay. And what will be the output? This y of z apparently will equal to what? x1 of z, right? x1 of z. So I can replace this y of z here with x1 of z here. Okay? Yeah. That makes sense? Yeah. And this z to the power of negative 1, if you move that to the right, this will become what? Z, that's right. It will become Z there. And u of z minus 4x1 of z plus x2 of z. Okay. Second one there is similar. Z x2 of z will equal to 5 u of z minus 3 y of z is x1 of z. Okay, so now we have this. Yeah, now we have this. Okay, so almost there. Oh, that diagram is annoying. Actually, I didn't use that. Okay, so the first one here. Okay, we want a difference equation. We want a state space model. So what if you take the inverse Laplace Z transform? What is the Z x1 of Z? Is what? x1 of k plus 1, right? K plus 1. Okay? Yeah, you might have the initial condition, but we're going to discard them. Okay? Yeah. And what's this guy here? That's u of k, but let's do this first. That's a negative 4 x1 of k. Over here, that's x2 k. And that u becomes u of z becomes u of k. Second one here is x2 k plus 1. And negative 3 x1 of k. And plus u of k. Right? Yeah. Okay, that's it. That's the state space model, right? And if you want to write it in a matrix format, so what would that be? Negative 4 here, 1 and here, negative 3 here, 0 and here.
You're missing a 5, right?
Huh?
The 5 u kit.
Oh, right. Yeah, 5 here. Yeah. And then 1, 5 at here, and u of k. Yeah, u of k. Is that good? Yeah, so that's the state space model here. Okay, and the output is y of k, right? Y of k equal to x1 of k. Okay, x1 of k. So output will be just 1, 0 here, x1, x2. Okay, x2. There's no d, right? Yeah. Okay. So this one here, in a different name, this is called nested programming method. Okay, nested programming methods. The most of the time, those names coming from the DSP, digital signal process, how they do the filter design. Okay, when you do filter design, ultimately you have to implement that right in either software or either hardware. So this is called nested programming. Now, this is actually a very important format here. This format here is so-called observable canonical form. So at this stage, you hear a very important name. Okay, so you might not, you don't have to worry about. So anyway, let me translate it. This is called observable canonical form. So basically refer to this one, okay? Refer to this matrix. Okay. It's called canonical observable form. And why is it called this name? We'll deal with that in later class lectures. Okay. Any questions? All good? Yeah. Yeah.
How many members in a group for a project?
Come again?
How many members in the group for a project?